Hi everyone, welcome back. In this video, we'll be talking about Stack Overflow. Okay, the title is really interesting, but today's challenge is an easy one. So we'll be going to Costco. So basically, Costco is another challenge that we will be working on microcorruption. Uh, Before I try to spoil on you what Costco is gonna be, so from the title you can just know that I'm gonna be talking about Stack Overflow. So I thought before just solving Cusco, since it's just a simple use case or a simple proof of concept of how we can exploit Stack Overflows, I thought why not I just explain for you Stack Overflows for complete beginners, for someone who don't know what a Stack Overflow is. Um, I think this video is going to be helpful for you. So what is Stack Overflow exactly? So to explain a Stack Overflow for you, I thought I would create a simple program in my computer just for you so that you can understand what Stack Overflows is. So basically we have a function that has a buffer. So the buffer has 10 elements or 10 characters or 10 bytes, and then you have to enter your name, and then you obviously just read your name into that buffer. Now the thing is that we have another function outside of the main, but we don't call that function inside of the main. Now the question is, by looking at this code, let's just try to run it just before we just take a look. If we run the code, we see that, so basically just before I run the code, so basically we have the code.c, and this is the binary I have compiled it using GCC. The compiler is GCC. So yes, so if we try to run the code, for example, if I give item wide, it does nothing. And basically, if you take a look at this function, so this is a function get shell that will give you a shell. So basically, a shell, for example, when you type in um, just a second. Okay, what does happen here? Yeah, there's just a little lag. Okay, if you just take a look, for example, if you input sh is a kind of, it's not bash, but it's kind of shell. So it's a shell that gives you, for example, specific stuff. For example, a bash is also a program. It's basically a program in a computer that can give you a lot of stuff that you can do. For example, ls is a command in bash, and so on. So basically, this is a function that gives you a shell. So basically, we don't have that function called in the main, but here's the thing. We will try to call that function. So the idea is, if you have watched my videos about reverse engineering and you have watched specifically the video about calling convention and that kind of stuff and how the stack is working and all that, I highly recommend that you watch that video. And if you haven't watched it, because I have explained pretty well how the stack layout is working exactly, and how the functions are called, and how the stack frames are built, and so on. So basically, this main function is going to be returning to some place. So the stack overflow, basically, guys, is based on the fact that we have to return to a specific function that we want. For example, in our case, we want to return to get shell. So basically, in the main, we want this main function to return to this function. So the thing is that if we go back into, for example, the sketch where I want to draw something for you, if you have remembered something, when we have talked about the stack layout in the calling convention video, if you remember with me, when you open up a stack frame, for example, this is the stack frame of the main. So this is the stack frame of the main. So we basically have the first thing that we do before opening up any stack frame, we push the return address, and then we push the base pointer. In our case, it's gonna be um, RBP or RBP, which is the base pointer, and then we start allocating local variables. So this is some local variables. And the thing is that the EBP or the RBP will be pointing to this place, and the RSP is going to be pointing to this place. So this is the stack pointer, and this is the base pointer. Now the thing is, for example, if we take this case, for example, if we try to just mimic what the computer is going to be doing, so we have the main function, and it has a buffer of 10 bytes. So basically, the local variables that it has in this case is only a buffer with a 10 bytes. So we can just call that, for example, let me just refresh the page. Yeah. So if we call this, for example, a buffer, then this is going to be the buffer with a 10 bytes of data. And then we will be having the base pointer, and then we will be having the return address. Now the thing is that since we are working using 64 architecture, and as you can see, all the registers are starting with an R because we are using a 64-bit architecture, which means that the registers are 64-bit size. Now the thing is that this base pointer in the stack, or this address specifically, is going to be 8 byte size, which means that all the addresses on the stack are divisible by 8, which means that, for example, um, if there are, for example, if since the buffer is on 10 bytes, obviously, there are some cases, or let's say there are some cells on the stack. So each cell um, is going to be having an address, and that address is going to be divisible by 8. So for example, if this address is 0x0, or let's say 0x 8, then the address before that it's going to be 0x 8 plus 8, which is 16. It's going to be 10, and so on. So basically, we keeps on adding the addresses that way until we get to the return address. Now the thing is that each address should be pointing to 8 bytes. Now that means that the RBP is going to be taking 8 bytes of size. And then the return address is going to be also 8 byte. So the thing is, if we can try if we can try to override the RBP and then override the return address by the address of the get shell, then we will be obviously returning to the get shell instead of returning to the main, or let's just say returning normally, because normally the main is also a stack frame and is called by other, let's say, code. So the main was called by other code. So basically, when you finish the main, you basically jump into another code. So instead of jumping into that other code, we want the main to jump to the get shell. So basically, this is the idea. So we have to overflow the buffer. So we are basically overflowing the stack. So that's why we call that vulnerability stack overflow. So we overflow the buffer, then we overflow the base pointer, we override the base pointer, then we override the return address by the address of the function that we want to jump to. Now the thing is that all that is possible because there is a vulnerability in the code. The vulnerability is because of this function. So if we take a look, and we can just read about that function quickly. So if we open up the manual about gets just to see, you see that get you a string from a standard input. So it's deprecated, and there is a description that says never use this function, which means that this function is really dangerous function because gets reads a line from the standard input, which is your keyboard, into the buffer pointed by s until either a terminating new line or end of file, which it replaces with a null byte. No check for buffer overrun is performed. You can see the bugs below. So this function is basically having a lot of bugs. We can just imagine how much dangerous this function you can it can do. So basically, this function have no limits on the size of the data that you can input. So for example, if you input 1 million bytes, it's not gonna be checking if you have inputted 1 million. As long as you have you as long as you are using it, you don't have limits on the amount of data that you can send to the program, which is a really dangerous thing. You should always check the amount of data that you want. For example, if you are allowing, for example, data to be of size, for example, 20, you should have the user, or you should check if the input of the user is 20 size. If it's not 20 size, you don't accept that. Those are some kind of constraints that are really important when working with this kind of stuff, especially in terms of security. It's really dangerous to give the user the user some kind of space so that he can do that kind of stuff. So, for example, in this vulnerability, as you can see, we have overridden, we have used the buffer, we have used the 10 bytes of the buffer. For example, we can send 10 eights, and then, for example, we can send, for example, 8 other eights just to override the RBP, and then we can, for example, just send another return address, which is, for example, 0xabcdef, and so on, which can be obviously the get shell address, just to return to that function and get a shell on the user. So this actually can let us do a privilege escalation. For example, let's suppose the program is running as root. So if we take a shell, so basically the process is running as a root, and if we try to call this get shell function, we will be running also as a root. So this is actually astonishing because it will be giving us a shell on the computer of the person that is having the program run on, which means that if I run the program on your computer and if you expose the program to the public and the program is vulnerable to this vulnerability, then everyone who has discovered that you have a vulnerability in your code by reverse engineering the binary, for example, if the binary is in public, then that person can have access to your computer because he can get a shell on it. So this is basically a simple scenario that can happen, but it does not mean that this scenario can have or can happen in real world. Yeah. Now, from a technical perspective, I have just explained for you what Stack Overflow is. Now, let's try to exploit that vulnerability, and to do that I will be using GDB. I have tried to use GDB just to let you just feel the vulnerability in front of you. So if we try to debug the code, so for example that we do the usual stuff. We try to see what kind of functions that we have. So we break in the main, break into the main. Uh, so if we try to run, this is basically the main if we have tried to run that, but to I don't want to keep scrolling around using the step. I want to break exactly after I give him the input. So I'm gonna be breaking there, and then if I take a look at all the breaks that I have, info break. So I want to delete the first one. If I take again, so we have now only one breakpoint. So if I run again, I'm supposed now that since the main is having, as you can see, this is just a simple call to a printf. Then there's this call to this just gets that's gonna be getting my input, and as you can see, my input is 10 bytes away from the base pointer, just like as you can see in this image. So if this is the base pointer, then if we just go up a little with a 10 bytes, which is 0xa, then we get the offset of the buffer. So this is basically the buffer. Then we get that buffer, and then we move eix0, and then we leave. Leave is gonna be actually cleaning up the stack, and then we return by just checking the top of the stack, which is the return address. We will try to see all of that in the GDB. So now, for example, if I want to enter my name, let's suppose I want to enter item byte. So as you can see, item byte now, well, so this is basically the layout of the stack. Those are the addresses that I have talked about, and as you can see, all of them are divisible by 8 because I'm using a 64-bit architecture. So this is the top of the stack. This is the address under the stack, and as you can see, we always have to add 8 in order to get to the next address. Now the thing is, for example, in this stack, I wanna know where the return address is. I wanna know where the RBP is, and I wanna know where my input is in order to know how can I build my attack exactly, or how can we exploit this vulnerability. So to know, for example, where the return address is, we can use info frame, which gives you an information about the stack frame that you have in front of you. So as we can see, the stack level is 0 because we are only on the main, we are not in another function. This is the frame. So what is really interesting is that the RIP is right now is in this address, which is this one, and the save at RIP, which is the instruction pointer that was saved before calling the main, is at this address. Now the other two interesting things is that the RBP is saved on this address on the stack, which ends with F0. If we go and try to check the F0, so this is the address. So this is where the RBP or the base pointer is saved. So if we go and check the base pointer, it should be having a 1. So yeah, and the instruction pointer is actually now having this one. So this is basically the return address. So the RIP is at this address on the stack. So if you go and check F8, so this is F8, and as you can see, it's in red because it's a special one because it's the return address. So this is basically where the main is going to be returning. So if we can, for example, change that value into the address of the function of the get shell, then we will be having a return to the get shell function. So basically now we have retrieved where the base pointer is, we have retrieved where the return address is. What rest is how we can retrieve where the offset of our input is on the stack. So as we have said, it's as you can see, for example, let's just go back a little. Just I wanted to show you something. For example, if I send Senora, for example, the thing is that if now I wanted to know where Senora is exactly in the memory, I can just use the find. It's a great function that comes with beta, which is an extension in GDB. So if I go and check Senora in memory, I want to find where Senora is in memory. So Senora is at this address on the stack and at this offset on the heap. Now forget about the heap. We want to focus on the stack. So it's at this offset. So now if I want to know how much data I have to send in order to get to the return address, which is at this offset on the stack, so we know now that Senora is at this offset on the stack, and we know that the return address is at this offset on the stack. If we subtract them together, if we subtract that from that, we get how much data we need to send in order to get to the return address. And it is supposed to be 18, since theoretically, as we have tried to explain that, we see that we have 10 bytes of data and we have the base pointer is going to be 8, and then with the return address. So we should be sending 18 bytes of data. That's theoretically. Now, in practice, let's see if that is right or wrong. There might be, for example, some other bytes, for example. We don't know yet. Let's try to subtract that from that and see what's gonna be happening. So if we subtract that from that, so this is the offset of Senora. Okay, so it's basically 18 too. Now this is a good thing. So our theory is good. Now if we try to exploit that, now the exploit is going to be as follows. So I have tried to write a simple payload generator. So we will be sending 18 bytes of data. I have just choose that A as an example. We can send, for example, B or A or whatever. And then we need to send basically where we want to be returning, which we have to retrieve just using, for example, info functions again. We have just to take a look at where exactly the get shell is. For example, get shell is at this address, which I have just put in here. So basically, p64 comes as a function from the pound module, which we have used a lot. Whenever you are, for example, playing pound challenges, you always just use pound. This pound is just a beautiful module that comes with Python. You can use it in a lot of challenges in crypto, in reverse engineering, in pound, in whatever. So p64 is gonna be just packing the return address as a 64-bit value, and then we're going to be printing the payload. So basically, if we try to run that, um, let's try to run that. Python 3 um, payload. Is it payload? Wait a second. Load gen.py. Okay, let me exit. Let me exit. Python 3 payload.gen. Yeah. So this is basically the payload. Now, well, we don't have to copy the two zeros. We don't need them. And if we try to again get into the program and debug it, so if we break into the main and we run, so if we disassemble the main, now we see that we have this address. So if we break into this address, well, the first thing to do is before breaking into that address, let's try, for example, to see what we can do. For example, printf, we finish from that. We step, and then as you can see, before reading the input, this is the return address. Now let's just step again, and we finish that. We send, well, it's not that input. We send this input. Now, as you can see, once we have sent the input, the return address have changed to the get shell function, which means that we have overflowed all the all the data before the get shell. Even the RVP should be now changed to that value. We can just check that out if we want. So the base pointer now is having that value, which means that the base pointer has been overridden. And then we have overridden the return address. Now, I suppose if we step one more step and then leave is going to be cleaning up the stack, which means it's going to be cleaning the stack frame for us and getting the base pointer, the old base pointer, which have been modified by us, obviously. So leave is gonna be cleaning the stack, and now we are gonna be returning to the get shell. And as you can see, now we are in the get shell, and we have successfully just exploited the stack overflow. Now, if we finish from that, we should be getting a shell. Yes. Anyway, yeah. So this is basically a shell, as you can see. So we have a shell now on the computer. So basically, we have called a function that is not callable in the main. So basically, we have returned from the main into another function that was not called in the main. So just by exploiting a vulnerability called Stack Overflow. I hope that you have learned something new basically just by watching me explaining for you Stack Overflow. And from a practical perspective, they have actually developed a mitigation against this vulnerability. The mitigation is called Stack Canary. They have built something like this. So basically, to mitigate or to defend themselves from such a vulnerability that is pretty old. I think it was discovered in 1990 or something. So they have built something called Stack Canary. So Stack Canary is basically if we take a look, so this is basically the return address. So this is the return, and in this place above the return, we will be adding some protection called canary. We have basically added some random bytes above the return, and now you find the base pointer, and this is the buffer. So basically, if you want to try to do the same attack on this kind of stack that was protected by the canary, you have to send 10 bytes of data plus 8 bytes of data plus another 8 bytes of data, and then to get to the return address. Now the thing is, there is another function that is gonna be checking if the canary was modified or not, because you will be obviously overriding the canary. So if you override the canary, then obviously we have detected that you have smashed the stack, and the smashing stack message is gonna be in front of you. Well, the thing is that we have successfully just exploited this code is because I have compiled it in a way that I have disabled the stack canary in order just to show you the stack overflow vulnerability, and you can check, for example, if the stack canary is there or not, just by using for example, pound check stack. By just using this function, you can check, for example, if these canary is there or not. So no canary is found. Um, I don't have to explain the other mitigations. You can check them out. Or maybe you can, for example, if we had another challenges that talked, for example, about the NX and the Pride, maybe I will just explain them for you. But for now, I hope you have just fully understood how the Stack Overflow vulnerability is working exactly. I think I've tried to make it simple as much as I can so that we can just try to work on Cusco. So now it's time to jump into Cusco. So let's see what we have. So overview. So we have fixed issues with passwords which may be too long. This lock is attached to the Lock ID Pro Hardware Security Module 1. So if you remember from the Hardware Security Module 1, if we take a look at the Microcorruption manual, so the Microcorruption manual has something to Yes, have something to talk about that one, which is the Hardware Security Module 1. Okay, so the lock ID includes several hardware security module interfaces along with the lock Pro. So the first of these is the Model 1. So the Model 1 of the hardware security module contains a simple interface which allows the microcontroller to test if an enter password is valid, which means by default the interrupt using that interrupt number will pass a given password to the HSM and will set a byte in memory if the password entered matches the stored password. So the stored password can be reset by detaching the HSM from the lock and attaching it to the Model 1 REST reset device, also included. So basically, our lock now is gonna be having another module, which is the HSM. So the MSP 430 is gonna be attached to two modules. The first model is is obviously the hardware security module that's gonna be testing the password, and the other one is the deadbolt. The deadbolt is actually the one that's gonna be opening up the door or not. So this is basically what a deadbolt is. This is actually It's actually just a thing um, that we use in order to open up the door or not. So it's basically like that. Yeah, this is what a deadbolt is. Anyway, so the Lock ID Pro is the first of a new series. Blah blah blah. So the Lock ID Pro contains a Bluetooth chip, allowing it to communicate with the Lock ID Pro app. Anyway, so there is no default password on the Lock ID Pro. Upon receiving the Lock ID Pro, a new password must be set by first connecting to the Lock ID Pro HSM to output port 2, connecting it to the Lock ID Pro app, and entering a new password when prompted. And then restarting the Lock ID Pro using the red button on the back. So Lock ID Pro Hardware Security Module 1 stores the login password, ensuring users cannot access the password through other means. And the Lock ID Pro can send the Lock ID Pro HSM password, and the HSM will return if the password is correct by setting a flag in memory. So the thing is that HSM takes two things. It's actually taking the password and taking the address where to put the answer if the password is wrong or right. So the thing is that since the password is actually stored with the HSM, that's actually might be a problem, but we will see how we can bypass such a problem. Anyway, if we try now to run the program, so it's saying that enter the password to continue, the password that's going to be tested by the HSM, I suppose. So for example, if we send back item byte, what do we have? So we see that the password is not correct and the CPU is out of range. Okay, so that means that he had returned. So for example, if we reset and we step again, we send for example 1, 2, 3, 4, 5, 6, 7, 8. I suppose that's an 8 since the password is between 8 and 16. We send that. Same problem. Okay, I think we should just read the code. So if we take a look at the code, so if we search for domain as the first thing, so we see there is a login. Okay, so he's calling a login. So this is something we have seen before. Um, okay, so where's the login? So this is the login. So just some stack alignment, aligning the stack to a new address. Then he is printing the enter the password. Remember the passwords are between 8 and 16 characters. So here's the thing. So since this is a challenge that I just as I had said about Stack Overflow, we have to basically focus on how he is reading the data. So he's gonna be reading 0x13 bytes of data, which is let's just go into Python, which is 48 of data. So he is saying that he wants a password between 8 and 16, and he is reading 48 bytes. Now, this is an attack vector that we can use. Now let's go and continue reading the code. So what do we have? So basically he's gonna be reading that into the stack. So this is the thing. So he's gonna be reading 48 bytes into the stack. Okay. Next thing that he's gonna be doing, he's moving that data into the register 15, then calling the test password valid. So we can let's just check this function out. So the test password valid is gonna be pushing the register 4, then passing that one moving what's on the stack to that register. I think the best way to debug that is just using some dynamic analysis. So basically, let's try to breakpoint there and see what's going to be happening. So if we continue, for example, let's send iron byte 1, 2, 3, 4, 5. So we hit the breakpoint. So what the register 15 now is having 43EE. Okay, let's go and see what the stack is having. Right now, um, there's something weird in here. What is our input? Hmm, did he accepted our input? Oh, wait a second. Let's try to just set a breakpoint there um before we get into the test function. Yeah, 1, 2, 3, 4, 5. Uh, okay, there is a problem. The stack pointer is not saving our input, which is weird. Okay, well, let me just suppose that he is right. 43 EE. His okay. Just a second. Reset that. Yes, because I'm just checking the hex encode input. My bad. Okay, it's cool. We don't have a problem with that. We can just create an input that is like that. I suppose I'm gonna be sending a bunch of A's, for example, by 16. Now those are 148. Okay, cool. Now we have our input, right? Okay. Um, that's nice. So those are the A's that we have sent. Now if we step into the test now, okay, so the test password valid is going to be pushing the register 4. So just saving what the register 4 was having. So the register 4 was having just a 0, okay? And then he's moving what's on the stack to the register 4. Hmm, okay. So this address is supposed, well, this is the input, and this is the return address that we will be returning to. Now he is actually pushing or moving what's on the stack pointer, which is that value, which is 3A, EA, I'm sorry, into the register 4. Okay, I'm just supposing that he's saving something. Then he's incrementing the register 4. Okay, that's supposed to be pointing to this address. Exactly. Then he's decrementing the stack pointer, which means that now he's allocating some other data. Then he's moving 0 to the register 4 minus 0x4, which means that he is gonna be subtracting 4 from this address that is pointing in here, and then he's gonna be subtracting subtracting 4 from the address that is pointing to this byte is gonna be getting us to this byte. Yes, so this is a 0. Now he's moving a negative value into the register 14. So this is basically a negative value. Negative value. We can just check that out just by using hex to integer. We can convert that. Come on, the website is too slow. Um, it's not too slow. Yeah, so it's a -4 basically. Okay, so we are moving -4 to the register 14. Then we are adding the register 4 to the register 14, which means we are subtracting 43. We are subtracting 4 from 43 EC. Okay, which gets us 43 E8, which is I suppose this one, this value. Okay, so we are pushing the resistor for 14, then we are pushing the resistor 15. Now we are just pushing actually the variable. So the resistor 15 should be having our password. Resistor 14 should be the memory or the address or the offset where we want to set the result. So this byte is gonna be our result. If the password matches the password that is on the hardware security module, then we are cool. Otherwise, it's not. Then we call the interrupt. Well, we don't have to dive too much in what the interrupt is having. And as you can see, we are moving 1 byte, which is at the offset register 4 minus 0x4, which is this byte. we are moving that in the register 15 as a result. And since the password does not match, it's gonna be a 0 obviously. And then we are sign extending that register. Well, sign extend is gonna be just for you, just to explain this instruction for you in case you have encountered it in other microcorruption challenges or even in ARM, for example. So SXT, which is sign extend, is basically gonna be extending the 7-bit and the value into the higher bits. For example, just for you to understand what the SXT is doing. For example, imagine we are having 1000 and we have 0001 so this is basically 1188. So this is just a value 8811. So if we put that into register 14 and we do SXT of register 14, it's gonna be given us, we basically take a look at the 7th bit, which is this one, 7th bit. If we take a look at the 7th bit, we actually gonna be making all the values who are higher than the 7th bit to that value exactly. So for example, if we have a 0 in here, we're gonna be having 0, 0, 0, 0, 0, 0, 0, 0, and then we will be having the other ones, which are 0, 0, 0, 1 and 0, 0, 0, 1, which are 1, 1, 0, 0. We can check that, for example, if you want in here, for example, we can try to, for example, set the register 15 equals to just to see the difference. For example, to see the difference, if we make this a 1, they should become FF because they will be 1 1 1 1 and 1 1 1 1 because the 7th bit is 1. So if we set it to 1, so let's set, for example, 0 0. So register 15 is gonna be equals to 0 0. Then it's gonna be F2. So since the 7th bit is 1, it should be equal to 1. So if we sign extend that and we see that it's gonna be FF F2. So this is basically what the sign extend is doing. So let's just go back a little. So PC equal to this address. We don't wanna we don't wanna open up the door yet by cheating. And set the register to 0, 0, 0. Okay. Healthy step, everything is cool. So we clean up the stack just by adding 8 to the stack pointer to go back to the return address. We pop the register 4 to get to the return address. And now we are at the return address we return. And we are now in the main. We test if the register 15 is equal to 1. So if it is a 0, we jump to the password is not correct. And we put that message. Now, here's the thing, guys. Basically, we don't have access to the hardware security module, since we cannot see what that interrupt is going to be doing how he's going to be testing exactly our password. We don't have access to that. The only thing that we have access to, if we take a look, is the main function. We basically called the login. So basically, when you call the login, you basically push the next address as the return address, which is 443C, and then you go into the login. And in the login, we spotted that there was a stack overflow vulnerability. Why? Simply because he said that he wants the password between 8 and 16, and somehow he is reading 48 bytes, which means that in the login, if we try to override the return address of the login function and return it, for example, to this beautiful function, which is the unlock door, then we can obviously return the program to the unlock door and just unlock the door without even having the right password. So the thing is, we need to find out where the return address is exactly in the stack, just as we have did with the program. We have to find the offset of our input to the return address in the stack. And once we find the offset, then we just have to put the return address of the function that we want to return to, which means that we have just to put 4446 as the return address instead of returning to the main in this case. Since we are calling the login, instead of returning to the 443C, we should be returning to this place. So this is basically how we can again exploit such a vulnerability. So to find out that address, we can just set a breakpoint in the main just to see what that address is going to be doing exactly. So if we continue in that, we see that this is a call. So this is the return address, which is 3C44. Why? Simply because if you go back to the main, the next instructions that's going to be executed after calling that function is going to be 443C. Just a simple behavior of the call. So he pushed the next address and then he jumped to the function. Now if you step, we see that we are now obviously in the login function. Now the thing is, I want to continue until I get the string. Now the thing is, I'm gonna be sending 16 bytes just to fill those addresses, as you can see. Well, before just sending the 16 bytes, let's try to send, for example, 2 bytes and see where the beginning of of our input, exactly where our input is exactly in the stack. This is basically what we want to know. So, for example, if I send 41, um, let me just take that. So, if we send that, as you can see, our input is now in here, and somehow since the obviously the input ends with a 0, it overrides already the return address. It overrided 1 byte with a 0. It's supposed to be 3C, but now it's overrided with a 0. Now the thing is, since we are reading a lot of bytes, which is 48, we can, for example, send that, and we add to it 64 and 44, which means that I'm gonna be returning to this function. So I'm gonna be overriding the return address with this one. Since the address is reversed, so I'm gonna be sending 46 and then 44 in order to get the right address to return to. So if we try this one, if we reset, and if we send this one, so as we can see now, the return address has changed. Now let's try to breakpoint before the login finishes, before it returns. Let's try to do that. So now we don't need those breakpoints anymore. So before the breakpoint, as you can see, the stack pointer now is pointing to this one, which is 43EE. If we step back, now just taking those 10 obviously those 10 bytes, since he was expecting from us to send 16 bytes, sorry, not 10, 16 bytes, we obviously land on the return address that we have set, and obviously once we return, boom, we return obviously to the unlock door. If we continue, we obviously just unlock the door. So basically we have exploited again a stack overflow. We overflowed the buffer, which is in our case the password, and we have overridden the return address to another return address, which is really interesting. Now if we want to solve that, we just have to send that, and we have solved it. A really interesting one. I see that the the proof of concept is much more harder than the challenge, but I hope you learned something new. Anyway, I think I'm gonna be trying as much as I can to finish all the microcorruptions together with you. Don't forget to hit the sub button. Don't forget to follow me on Twitter, and don't forget to join the Discord too. The Discord server, yeah. So yeah. Yes. Have a nice day. Bye.